This lesson deals with a complex power system with long wires. You can find these notes in the ECE202 ebook in chapter 16, starting on page 9. Suppose that we take an AC induction motor that has an impedance at 60 Hertz of 3.32 plus J 2.023 ohms. And suppose that we connect that with 1,000 feet of 3-gauge copper wire, which has an impedance at 60 Hertz of 0.197 plus J 0.0588 ohms. Can you find the voltage across the load, the current through the load, the real power absorbed by the load, the reactive power absorbed by the load, the real and the reactive power absorbed by the wires, and then the real and reactive power that's generated? Can you also find the power factor? So here's a sketch of what that's describing. Now remember, we have a piece of wire that's going to take us to the motor, and a piece of wire that's going to take us back. So we've got twice the value of that impedance. 3-gauge copper wire is a 1/4 inch diameter. I have a 1-loop circuit here, so pretty easy in terms of our calculations, and then we'll relate this to our real and imaginary power. Okay, so if you want the current in the load, just simply have the voltage here divided by the total impedance. So that's 240 at angle 0, divided by the sum of the real parts, which is 3.714 ohms, plus the sum of the imaginary parts, which is J 2.1406. Putting this into polar form, we get a magnitude a little bigger than either of these two, and we're going to be in the first quadrant with an angle less than 45 degrees because this is shorter than this. So 4.2867 at angle 30. 240 divided by that magnitude is 56, and the angle is 0 minus 30 degrees. And that's going to be in amps RMS. The voltage across the load simply would be the impedance times the current, which is 3.32 plus J 2.023 times the 56 at angle minus 30 degrees. Putting this into polar form, I get 3.8878 at an angle of 31.36. Again, first quadrant. Angle is going to be less than 45 because this is shorter than this. Multiply the magnitudes, you get 217.72 volts RMS, and the angle is 31.36 minus 30, so 1.36. So we lost a little bit of the voltage, and have a little change in the angle in taking the voltage that we're generating and delivering it to the load. So what I want to show you is the dramatic consumption of power of the wires. So let's calculate, first of all, the real and reactive power of the load. From our previous formulas, that's going to be the magnitude of the current squared times R sub L, which is 56 amps, 3.32. And that's going to be equal to 10.41 kilowatts. Again, the units on the real power is watts. The reactive power is magnitude of the current squared times the reactance, X sub L. So 56 squared times 2.023. And that's 6.344 kilovars. And again, the unit here on reactive power is vars. And so our complex power is the real plus the imaginary, and that's going to be in the units of volt amperes. Take a look at the power that's dissipated in the wires. Now again, we've got a wire going to the load, we got a wire coming back, so the power that's absorbed by the wires, the real power, is the magnitude of the current squared times the total resistance. And that turns out to be 1.236 kilowatts. That's comparable to a toaster oven. We're losing a lot of power in the wires in just 1,000 feet of wire. The reactive power is the current magnitude squared times the reactance of the line. Again, we've got one going and one coming from the generator, and that gives me 368.8 vars. Complex power then is the real part plus the imaginary part in volt amperes. Let's calculate the complex power that's generated. That's going to be the voltage of the generator and the current coming out of it conjugate, which is also the current in the load. So we're going to change the angle here from minus 30 to plus 30. So multiplying those two, I get 13.4 K. And the angle is to be 30 degrees, and putting that in rectangular form, I get 11.64 K plus J 6.72 K. The units here are volt amperes. So my real part is 11.64 kilowatts, and my imaginary part is 6.72 kilovars. Now let's do a power check. Let's see if the power generated is equal to the power absorbed. We've proved that theoretically, but let's just double check that. All right, so the real power absorbed by the circuit is the power in the load and the power in the lines. And that's 10.41 kilowatts plus 1.236 kilowatts, so 11.646 kilowatts. And that equals what we found with the generator. The reactive power for the load and then the line was 6.344 kilovars plus 0.3688 kilovars, giving us 6.7128 kilovars. That's equal to what was generated. So our power checks. The power generated real equals the power absorbed real, and likewise for the imaginary. Lastly, we're asked to calculate the power factor, which is the cosine of the angle theta, which is the angle of the voltage minus the angle of the current. So we had an angle on the voltage of 1.36, The angle on the current was minus 30 degrees, so subtracting that I get a 31.36. Cosine of that is 0.854, but we can't tell whether this quantity is positive or negative by just looking at this result, but by looking back at the angle. Since it's positive, then it's a lagging power factor. And this is an example of a complex power system with long wires. We're going to revisit this example as we make some changes to our connection between the generator and the load.